In this video, we'll start our discussion of gases by talking about what we mean by pressure. We'll introduce the ideal gas law and look at change of state problems. So let's talk about measuring pressure. Pressure is usually measured with a device called a barometer. The way this works is you take a tube where the tip is evacuated, so usually you'd fill it completely with the substance, and you have one open end, and then you'd invert it, in this case, into another container of liquid. So if you do this with a tube of mercury, we can think what would happen. So the liquid in this tube, when it's first filled up, would want to move down due to the force from gravity. Now we know that liquids, while they don't have a fixed shape, aren't compressible. So when this moves down, the free liquid in the dish has to also move back up. And so if gravity was the only force involved, eventually this all would just level out at the same level in the dish. However, there's another force that's involved, and this is pressure from the atmosphere. And the pressure is going to be a force per area, and what this comes from, in terms of chemistry, are actually the gas particles floating around in the atmosphere. So you can think about these, maybe for one analogy, if you've been to like a kid's birthday party, or maybe your own birthday party recently, you go to a bouncy house and you have a whole bunch of kids bouncing around. They're going to bounce off the sides, bounce off each other, whatever. That push against the barrier is a force due to motion. And so if we have a bunch of gas in the atmosphere that's bouncing around, on average as it collides with the surface of the liquid, there's going to be some force pushing down. So while gravity is pulling on everything the same way, the atmospheric gas is exerting pressure on the exposed liquid, but since there's a vacuum up here in the tube, there's no force from pressure in the top of this evacuated barometer. And so what will happen is the force, or the pressure from the atmosphere, will act upwards on this column, again since liquids aren't compressible, and we'll end up with a height of the liquid, where the mass and everything in one column and the force of gravity is exactly canceled out by the pressure pushing it up. For mercury, the height that this will be for the liquid is 760 millimeters when we're under regular pressure based on the amount of gas in our atmosphere. So again, this column of mercury in the tube is going to be supported by the air pressure. And if we had higher pressure, so if we put this in a pressurized chamber, more pressure would mean an even higher column of mercury. The most common unit of pressure that we're going to use is at sea level, is a pressure of 1 atmosphere. So this again, 1 atmosphere is a unit of pressure that's a force per area. There's other units of pressure. One common unit is torr, and this is directly related to that millimeters of mercury. So 1 atmosphere of pressure is equal to 760 torr of pressure. If you need to use this conversion factor, you'll be given to it on our test. Okay, so let's talk about some properties of gases. So we know that they're going to exert a pressure from the bouncing around molecules. There's some other things that we'll want to think about for gases. We can think about the volume, how much space the gas is going to occupy, its temperature, and we can kind of think that this might have a role with pressure when you're thinking about the temperature having to do with how fast the molecules are moving. And we also have the number of moles of gas. And the ideal gas law actually relates all of these factors and is given by PV equals nRT. When you're reading through this chapter in many chem books, they build up all these relationships between each of these individual properties, so things like Raoult's law and stuff like that. You don't actually need to memorize any of those individual laws because it's all contained in the ideal gas law. So when you're looking at this, in order to derive any of those other laws, what's important is to know the relationship between all the variables. And that's based on where they are with respect to each other in the equation. Since these two sides have to be equal, we can think about how volume and temperature are related. So if we increase volume, for example, for these to stay equal, would have to also increase the temperature. Another way to say this is that volume is directly proportional to the temperature. They'll move in the same direction with the same magnitude. We can ask about how pressure and volume are related, and we can see in this case, since they're on the same side of the equation, if they're going to have to stay equal to nRT, if we raise the volume, we have to decrease the pressure. Or we could say that the volume is inversely proportional to pressure. And this is useful to know so we can qualitatively tell how a reaction might change if we change the volume, the temperature, the pressure, and we can also think about changing the moles of gas. So you just watch where everything is with respect to each other in terms of this equation, and you can tell whether they're directly proportional or inversely proportional. One thing we haven't done yet is define the units in the ideal gas law, and for this we need to talk a little bit about absolute temperature. So if we're thinking about just temperatures, negative 273.15 degrees Celsius is literally the lowest possible temperature. That's the complete absence of heat. You can't get any colder than that. This is also called absolute zero. So the temperature scale that we like to use for most of these equations is actually the Kelvin scale that sets absolute zero to 0 degrees Kelvin. And so if we wanted to know the temperature in Kelvin, it's just going to be the temperature in Celsius plus 273.15. When we're using the ideal gas law, and actually for almost every equation that we use in chemistry, if you're given an absolute temperature, you should use the Kelvin scale, not the Celsius scale or the Fahrenheit scale. For the units of temperature to work in most of these equations, it needs to be in Kelvin. The one exception to this is if you have a delta T, so a change in temperature. For that, you can get away with Celsius. But if you always use Kelvin, you'll never be wrong. The next thing we have to define is what we mean by ideal when we're talking about ideal gases. And for gas to be ideal, there should be no interaction between the gas particles. That means when these things are flying around, they can't feel an attractive force to each other. The other approximation we make is that they occupy no volume, so we assume they're just tiny specks or relatively small gases. And if these are true, then all the gases will behave the same way. We don't need to worry about what the compound is. They'll still all follow the ideal gas law. So you can think about the gases that wouldn't follow the ideal gas law, or when we can get interactions, if things are really cold, they start to freeze. So that would increase the interactions between the particles. And if we have really big particles, those will also be non-ideal. For most gases that we experience, though, the ideal gas law is a good enough approximation because regular room temperature is about 295 Kelvin, which is hot enough for there not to be interactions between most gas particles, and most of the things that we're going to experience as a gas are going to be small enough that we don't have to worry about that. The other unit we need to talk about is the gas constant, the R, and this actually depends on the units that we're looking for and the type of equation that we're using. If you look on the information page, you'll see these two values for R, and if you look on Wikipedia, you'll actually see a whole bunch more. And so the two different values we see are this version, 0.08206 liters atmospheres per mole Kelvin, and the other one we see is 8.314 joules per mole Kelvin. And if you look at these compound units carefully, you'll see that they're related, but interconverting between the two does change the value. So when we're picking an R for our equations, we need to pick the one where the units will give us the value that we want. For the regular ideal gas law, where we have PV equals nRT, we can see what the values would usually be, and that'll help us with the problem. So if we have pressure and volume, pressure is usually going to be in atmospheres, volume is going to be liters, N is going to be in moles. We have R and T is in Kelvin. So if we want to cancel out the moles in Kelvin to get atmospheres and liters, when we're using the ideal gas law, we'll usually use that version of R. So again, when you're doing these equations, just look at the units given in the problem so you can pick the right value of the universal gas constant. The last thing that you'll often see in these problems that we need to define is standard temperature and pressure. And this is a typical value given, often abbreviated as STP. The standard temperature is going to be 0 degrees Celsius. Remember, that's 273.15 Kelvin. And the standard pressure is 1 atmosphere. So we can use the ideal gas law in our first sample calculation to calculate the volume of a mole of an ideal gas at STP. So we have PV equals nRT. The pressure we're given as standard as 1 atmosphere. The volume is what we're trying to find. we're given that it's 1 mole of gas and that the temperature is 273.15 Kelvin. We just need to make sure we pick the right value of R, and this is the one that's going to give us with liters atmospheres, so this will be the 0.08206. And if we solve for V, we get the volume of a mole of ideal gas at standard temperature and pressure is 22.4 liters. The last thing we'll look at with regards to this equation in this section are types of calculations where we're seeing a change of state. And this is for when we go from one state, so one pressure, volume, moles, and temperature, to another new state. And there's a trick to converting these because R is always a constant. So if we solve for R, we can see that the pressure times the volume divided by the moles times the temperature is always going to be equal to the gas constant, no matter what these are. So even if we change all 4 of them, they'll still always equal R. So if we have 2 different equations that both equal R, we can combine these equations to set up a change of state equation. So if we do this, isolate R and set them equal to each other, we get that the pressure from one state times its volume divided by the number of moles times its temperature. Since that's equal to R, it's also equal to the pressure of the second state times its volume divided by its moles and its temperature. So PV over NT1 will be PV over NT2. So if you're seeing a situation where we're changing any of these, you can just set these two equal to each other and solve for the unknown variable. If there's something that you don't know what it is, but you know that it's also not changing, so say you're not given the temperature, but you're told the temperature is constant, you can simply leave it out of both sides. Since it's constant, it's not changing, and you can save yourself a little bit of work. So let's look at an example of this. We have a weather balloon that's filled with helium, which usually behaves as an ideal gas since it's very unreactive, and it has a volume of 1.2 times 10 to the 4th liters and 1 atmosphere at 30 degrees Celsius. What we're going to do is let this balloon rise to an altitude where the pressure is now lower and the temperature is much colder. And what we want to find is the volume of this balloon at the new altitude. This assumption here that the pressure is equaling the external pressure is just so that we can use the pressure at the altitude. You'll notice, since we have a balloon and it's rising up, something we can think about that won't change is the amount of gas in the balloon. So the moles is going to be fixed. So when we set up this equation, we have P1V1 over N1T1, P2V2 over N2T2. Remember, the moles aren't going to change, but we are changing the pressure and the temperature, and we want to find the volume. So our initial pressure is 1 atmosphere. Our initial volume is 1.2 times 10 to the 4th liters. And our initial temperature is given in Celsius, but remember we have to convert these to Kelvin. So that's 303.15 Kelvin. And that's going to equal to our final pressure. We're trying to find our final volume and divided by our final temperature, and we have to remember to also convert that to Kelvin. If we put V2 on one side, we get a final volume of 1.7 times 10 to the 4th liters. So to wrap this up, we'll give you a chance to practice another one of these problems. So take a look at this problem and see what you think the final pressure of this container will be. And the answer is 3.75 atmospheres. Let's see how we got that. So here we have an initial pressure, we have an initial volume, and an initial pressure. So P1V1, 3 atmospheres times 1.5 liters. And if we think about N1 and T1, you'll notice the moles aren't given, but it's in a closed container, so it's a constant moles. And even though temperature is not given, it's telling us that it's a constant temperature, so this is a fixed temperature. We have a final pressure that we're trying to find, and a final volume, 1.2 liters. And again, we know the moles and temperature are constant, so those will cancel out on both sides. And we're just left with 4.5 is equal to P2 times 1.2. And so the final pressure is equal to 3.75 atmospheres.